Yeah, it says something like this. This Google Meet is being recorded. If you do not have permission to be recorded, please turn off your camera and microphone when recording is in progress. You may not download the recording or in any way keep the recording, including taking screenshots or pictures or copying the video. You may not distribute any images depicting another student or staff member. There we are. Now you've been duly warned. Okay, so the plan for today basically is we're going to quick go over naming the valley and polyatomic ions. Make sure we review the bond type. There's a name called formula units. We'll just make sure we understand. Check over Lewis dot structures, check over octet. I would ask that you please make sure that if something does not make sense, you ask questions. All right, unless you're not legally allowed to be recorded. Okay, all right, so I would ask that you guys pin me, if you would, for the next bit so that you can see it clearly. And let's get started. Okay, so first bit, the valley and the naming. I had a couple of people come into, support yesterday, got some help. Here's what I want you to think about with the valley and naming. I apologize. Somebody in one of the two classes asked me to make a video of this already, and I apologize. It's been a bit crazy. So, let's see. First of all, if it's a normal bond, like it's somebody in one of the two towers and somebody in the other tower, 2, 3, 4, 5, all right, and there's somebody over here with somebody over there, like magnesium gets together with chlorine, then we're just going to call it magnesium chloride. Very simple, very easy. All right, because there's only one way for them to get together. Now, if I asked you for the formula for that, you have to notice that I messed up. You have to look at magnesium and go, okay, magnesium's over here, and it's in that +2 column. Chlorine's over here, and it's in that -1 column. If you've forgotten, reminder, the first column is +1, the second column is +2, the third column is +3 if we skip the valley. The next one is +4 or -4 coming in from the other side. These guys are boring. Don't take them to parties. They do nothing. These are -1, -2, and -3. Okay, so I'd go real quickly. I'd go, okay, magnesium is 2+, chlorine is 1-, so I'm going to need to go 2, 1, all right, and I swap down and I get magnesium chloride. Review from previous. Okay, now the problem lies here in the valley, because here in the valley, there's multiple possibilities. All right. The example I used yesterday is I have a friend named Mike. I have about 6 friends named Mike. All of them are named Mike. You know, none of them go by Michael. None of them go by Mikey. They're just Mike. And so you got to know which Mike you're talking about. For instance, I might say that I've got a compound FeCl3 and I have a compound FeCl2. And I have to distinguish between the two of them because they're both Fe. They're both Mike. So I go over here and I go, okay, chlorine's -1, but there are 3 of them, so that's -3. The whole thing is neutral because it's not listed as an ion, so it has to end up as 0. And so the iron must be +3. Over here, same thing, -1 for the chlorine. There are 2 of them, and that's -2. So therefore, the Fe must be +2. So we would name this iron 3 chloride, and this one iron 2 chloride. Okay, so that just is, we need to be able to distinguish between the two. Now I can the worst I can do to muck about with you a bit would be to do something like this, where I go, I don't know, let's say I said Mn, what's a true one for that? Mn2s3. Mn2s3. Well, no big deal here, actually. I just look at the sulfur, and I say, okay, sulfur is -2 because it's right here. All right. but there are 3 of them. That makes -6. Now, the MNs, if we want the whole thing to be neutral, since there's no charge here, this MNs, it all has to add to 0, so the MNs must give me 6. But, 1t, there are 2 of them, so if I get 6 pluses from 2 things, each one must be +3. Does that make sense? The orange is a little hard to see. Let me redo that real quickly. -2, so -6. We want the whole thing to be 0, +6, so +3. So now we're going to name this thing manganese 3 sulfide. Okay, that's probably the most challenging thing I could possibly throw at you. And I'm not going to throw much of any of that at you. I just want you to know how to name these things so that if you get in a chemistry situation, you can do it. Questions, problems, concerns? Okay. And I know it's a little intimidating to be recorded. After the 100,000th time being recorded, you get kind of used to it. Okay, so if you do have a question, please hold on to it and ask it later, or ask it now. I don't care. Okay, quick review. Bonding types. As we said in the warm-up, we look at the periodic table. All right. There's this other table called the table of electronegativity. That's a big word. All right, 1, 2, 3, 4, 5. Okay, and so we've got numbers. The highest number on the whole chart is fluorine. The lowest number on the whole chart is francium. All right, and the differences between them tell us what kind of bond. If we take 2 atoms and hook them together like we did in the warm-up, where we had, what do we have in the warm-up?
Is it ionic?
Precisely. All right? Because if they're way far apart, anything that a difference of 1.6 or up is ionic. Okay, so if fluorine got together with francium, that's a difference of 3.3. That's big time ionic. Fluorine kicks his butt, takes francium's electron. It's not getting it back. Okay, on the other hand, the other example we used was nitrogen and oxygen. And if you look at oxygen, it's 3.5 and nitrogen's 3.0, a difference of 0.5. That is not ionic. That's covalent, but it's not really perfectly covalent. They're not sharing nicely. So 0.3 or 0.2 down is really, truly covalent. Anything in the middle is polar covalent. And that's important because polar molecules are important, all right? Because polar things dissolve in other polar things. And non-polar things dissolve in other non-polar things. It's like if you ever get oil on your hands, if you work in your car on the weekend and you get oil all over your hands, you can't get it off with just plain old water. Won't work. Okay? And so all you do is you look at a bond and you say, okay, if I've got NH3, I look at N, 3.5. I look at hydrogen, 2.2. And the difference in the bond, 1.3, tells me it's strongly polar. So that means that the electrons are going toward the end. Now, the big difference is there's just one thing I haven't told you yet, and I just want to put that out there. When it's ionic bond, they don't call them compounds. They have this word formula unit. And you might see that on a test or on a lab. So formula unit is just referring to the same thing ionic as if when you say compound for a covalent bond. That's all. No big deal. So when you see it, don't panic. Okay?
Wait, what was the difference between the polar covalent and the regular covalent?
Okay. Picture, okay. As far as the number or as far as the physical difference?
The number. Well, both.
Okay, the number, anything that's like 0.3 or smaller, that's considered covalent. Anything that's like 0.3 to about 1.5, someplace in that range, is polar covalent. Now, what does that mean? That means when two things are bonded together, all right, here's an example. If the two things are bonded together, the electrons are being shared between those two. But picture it like a tug of war, all right? This guy's fighting with that guy for the electrons, okay? In this case, this is nitrogen, that's hydrogen. The nitrogen is sort of winning. So the electrons are spending more time over here than they are over here. So that means this side gets kind of negative because the electrons are over here. This guy gets less negative, more positive because the electrons aren't over here as much. And then if we do that again and again, all right, too much time in Frederick County, all right, we get something looks like that where the electrons are going this way and the electrons are going that way and the electrons are going that way. All right. And so you see that all the electrons are ending up over this end of the molecule. And the electrons are less so at this end of the molecule. And so this thing is a polar molecule, not just a polar bond. Okay. The electrons are all going one way. They're ending up here in the top as opposed to the bottom. So if you can see a side that's positive and a side that's negative, then it's polar. If I had some other molecule, not ammonia, and it looked like that, where it's flat and the electrons are all going in, there's no polarity to that because it doesn't have a side that's positive and it doesn't have a side that's negative. You see it?
Yeah, thank you.
Yeah, sure. That's why I'm here. All right. Okay. So that's types of bonds. Next one.
Wait, can you do one more like example? Sorry.
Absolutely. No. Please. That's what. Thank you. I love it. Responses. Feels good. Okay. So if I give you an example, if I give you, I don't know, phosphorus here, and phosphorus is bonded to chlorine. I'm going to actually, phosphorus is over here. So I have to look and say, what's the electronegativity for those two elements? All right. So I would look, let me, did I keep the P table open? Yeah. So I'm looking on my P table. You can't see this. I don't know if the guys on the video, I don't know if you're going to be able to see it or not. So I look at phosphorus and I look at its electronegativity. So there's phosphorus hooked to chlorine. I look at the electronegativity of phosphorus, about 2.2. I look at the electronegativity of chlorine, it's about 3.1. Okay. So I go, okay, subtract, do the higher level math. I get 0.9. Okay. Now I just said if it's ionic, it's going to be 1.6 or bigger. If it's covalent, perfectly covalent, nice even kind sharing, it's going to be 0.3 or down. So this guy here, that bond is polar. And the chlorine is on that end. And so the electrons are going this way. They sometimes show it like a plus sign and a minus sign, and then they draw the arrow like that. So you sort of said the electrons are going that way. Does that help? Yes, no?
Yeah, thank you.
Okay. Now let's look at the next piece of that. Let's look at the electron dots. Okay. So we've got phosphorus here in this column. So it's P1, 2, 3, right? 4, 5, 6. So it's P3. So it's got 5 dots. So I'm going to give it 1, 2, 3, 4, 5 dots. Chlorine has how many? Chlorine's over here, it's P5. So it's going to have the 2 in the S and the 5 in the P, so it's going to have 7 dots. So it's 1, 2, 3, 4, 5, 6, 7. And the same thing, we're going to need another chlorine and another chlorine to make this thing full up. Okay, now we look at the shape. We look at the shape. So there's the electron dot structure. This should get easy because you'll just have to practice it. All right, the electron dots. Now we look at the shape and we notice that there are 4 things around the central atom. There's 1, 2, 3, 4. And we notice that phosphorus has its octet rule. It has its 8 electrons. Everybody up here in this corner, they want to be octet. Okay, so it's got 4 things around the central atom. So it's going to be like this guy here with 4 things. But one of them is an electron pair. So it's going to look like this guy here because the electron pair is up there, but we don't represent it. So it's not flat. So the electrons are going toward the chlorine, toward the chlorine, toward the chlorine. So this part's going to be negative-ish. This top bit's going to be positive-ish. So this will be a polar molecule. Okay? Now, stop sharing. I don't know how this is going to work on the video. I'll have to look. Never actually tried sharing at the same time. We'll see. All right. Now, in case that was all covered up by the sharing, since it's got 4 things around the central atom, I'm going to say this again, and I apologize. I'm doing this as much for the video, but it also help you guys. All right. Anytime you got 4 things around the central atom, it goes to this tetrahedral kind of shape. But then if some of them are electron pairs, it's going to be like this shape where it's a trigonal pyramid, like this. Okay, where the one's up higher than the others. If it's got 2 unbonded pairs of electrons, like water, all right, it's going to take these 2 away, and you're going to see a bent shape. It's going to look like that. Okay. Now, that, folks, is pretty much what you need to be able to deal with to do the lab and so forth. So here's what I'm asking of you for the rest of the period. First of all, I'm going to, unless somebody has questions for the good of the whole group, I'm going to turn off the recording. Okay, so here's what we're going to do. Let me shut this down.